Grounding and bonding are two distinct but essential concepts in electrical systems, working together to ensure safety and prevent electrical shock. Grounding provides a path for fault current to return to the source, tripping a circuit breaker or fuse and energizing the circuit. Bonding, on the other hand, ensures that all metallic parts of an electrical system are at the same electrical potential, minimizing the risk of shock if someone touches two different metallic parts simultaneously. Let's delve into the specifics of each. Grounding refers to connecting an electrical circuit or equipment to the earth. This connection provides a lower impedance path for fault current to flow back to the source, such as the transformer. The main purpose of grounding is to protect people from electrical shock and to prevent damage to equipment in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded metallic part, such as the metal enclosure of an appliance. Without a proper grounding system, the fault current could flow through a person who touches the faulty appliance, resulting in a potentially fatal electric shock. The grounding system consists of several components, including the grounding electrode conductor, and the equipment grounding conductor. The grounding electrode is a conductive rod, plate, or other object that is buried in the earth and provides a direct connection to ground. The grounding electrode conductor connects the grounding electrode to the neutral busbar in the main electrical panel. The equipment grounding conductor provides a path for fault current to flow from the equipment back to the main electrical panel. There are different types of grounding electrodes recognized by the National Electrical Code, or NEC. The most common types include ground rods, ground plates, and metal underground water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. Ground plates are typically made of copper or steel and are buried horizontally in the ground. Metal underground water pipes can also be used as grounding electrodes, provided they meet certain requirements specified in the NEC. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. It is important to ensure that the grounding electrode conductor is properly sized to safely carry the maximum fault current that could occur in the system. The equipment grounding conductor is another critical component of the grounding system. It provides a path for fault current to flow from the equipment back to the main electrical panel. The equipment grounding conductor is typically a green or bare copper wire that is run along with the circuit conductors. It is connected to the metal enclosure of the equipment and to the grounding busbar in the electrical panel. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Table 250.122 in the NEC provides guidance on selecting the appropriate size of the equipment grounding conductor based on the size of the overcurrent protection device. Bonding, on the other hand, is the process of connecting all metallic parts of an electrical system together to create a low impedance path for current to flow. This includes metal conduits, metal enclosures, metal water pipes, and other metallic parts. The purpose of bonding is to ensure that all metallic parts are at the same electrical potential. This minimizes the risk of electric shock if someone touches two different metallic parts simultaneously. For example, if a live wire comes into contact with a metal conduit, the conduit will become energized. If the conduit is not properly bonded to other metallic parts, a person who touches the conduit and another grounded metal object could receive an electric shock. However, if the conduit is properly bonded to other metallic parts, the fault current will flow through the bonding conductors, tripping a circuit breaker or fuse and energizing the circuit. Bonding is achieved by using bonding jumpers, which are short lengths of wire or metal straps that connect different metallic parts together. Bonding jumpers are typically made of copper or aluminum and are sized according to the requirements of the NEC. The NEC specifies bonding requirements for various types of equipment and systems, including service equipment, paddle boards, and metal water pipes. For example, Section 250.92 of the NEC requires that all service equipment be bonded together to form a solid electrical connection. This includes bonding the neutral conductor to the service equipment enclosure and to the grounding electrode conductor. Section 250.94 of the NEC requires that metal water pipes be bonded to the grounding system. This is because metal water pipes can provide a path for fault current to flow back to the source, and bonding them to the grounding system ensures that they are at the same electrical potential as other grounded parts. The size of the bonding jumpers is determined by the size of the circuit conductors or the equipment grounding conductor. Table 250.102 in the NEC provides guidance on selecting the appropriate size of bonding jumpers based on the size of the circuit conductors or the equipment grounding conductor. It is important to ensure that bonding jumpers are properly sized to safely carry the maximum fault current that could occur in the system. Grounding and bonding are often confused, but they serve different purposes. Grounding provides a path for fault current to return to the source, while bonding ensures that all metallic parts are at the same electrical potential. Both grounding and bonding are essential for electrical safety and are required by the NEC. In addition to the general grounding and bonding requirements, the NEC also specifies requirements for specific types of equipment and systems. For example, Section 250.146 of the NEC provides requirements for grounding and bonding receptacles. This section requires that all receptacles be grounded to the equipment grounding conductor. This ensures that if a fault occurs in an appliance plugged into the receptacle, the fault current will flow through the equipment grounding conductor, tripping a circuit breaker or fuse and de-energizing the circuit. Section 250.148 of the NEC provides requirements for grounding and bonding lighting fixtures. This section requires that all metal parts of lighting fixtures be grounded to the equipment grounding conductor. This ensures that if a fault occurs in the lighting fixture, a fault current will flow through the equipment grounding conductor, tripping a circuit breaker or fuse and energizing the circuit. Section 250.160 of the NEC provides requirements for grounding and bonding swimming pools. Swimming pools are particularly hazardous environments due to the presence of water and the potential for electrical shock. The NEC requires that all metal parts of the swimming pool, including the pool structure, the metal conduit, and the electrical equipment, be bonded together to form a solid electrical connection. This ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. In addition to the bonding requirements, the NEC also requires that swimming pools be equipped with ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect small amounts of current leakage and trip the circuit, preventing electrical shock. GFCIs are required for all receptacles within a certain distance of the swimming pool, as well as for the pool pump motor and other electrical equipment. Proper grounding and bonding are essential for electrical safety. By providing a path for fault current to return to the source and by ensuring that all metallic parts are at the same electrical potential, grounding and bonding help to prevent electrical shock and protect people from harm. It is important to understand the differences between grounding and bonding and to ensure that all electrical systems are properly grounded and bonded in accordance with the requirements of the NEC. When working with electrical systems, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment such as rubber gloves and safety glasses, and energizing circuits before working on them. It is also important to use properly insulated tools and to avoid working in wet or damp conditions. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work for you. A qualified electrician has the knowledge, skills, and experience to safely install and maintain electrical systems. They can also ensure that your electrical system is properly grounded and bonded in accordance with the requirements of the NEC. In summary, grounding and bonding are two distinct but essential concepts in electrical systems. Grounding provides a path for fault current to return to the source, while bonding ensures that all metallic parts are at the same electrical potential. Both grounding and bonding are essential for electrical safety and are required by the NEC. It is important to understand the differences between grounding and bonding and to ensure that all electrical systems are properly grounded and bonded in accordance with the requirements of the NEC. Always follow safe work practices when working with electrical systems and hire a qualified electrician if you are not comfortable doing the work yourself. Now let's expand further on specific aspects of grounding and bonding, focusing on common scenarios and applications. Firstly, consider the grounding of electrical panels. Electrical panels, also known as load centers or breaker boxes, are the heart of an electrical distribution system. Proper grounding of the electrical panel is critical for safety. The panel's metal enclosure must be connected to the grounding electrode system via the grounding electrode conductor. This connection ensures that the panel is at ground potential, reducing the risk of shock. Inside the panel, there are typically two separate busbars, the neutral busbar and the ground busbar. In the main electrical panel, the neutral busbar is bonded to the panel enclosure and connected to the grounding electrode conductor. This is the only point where the neutral and ground systems are connected. In subpanels, however, the neutral busbar must be isolated from the panel enclosure and the ground busbar. This prevents unwanted neutral current from flowing through the grounding system. The equipment grounding conductors from all circuits in the panel are connected to the ground busbar. These conductors provide a path for fault current to flow back to the source, tripping a circuit breaker or fuse. Secondly, let's discuss the bonding of metal water pipes. Metal water pipes are often used as grounding electrodes, but they must also be properly bonded to the electrical system. The NEC requires that metal water pipes be bonded to the grounding electrode system within 5 feet of where the pipe enters the building. This bond in connection ensures that the water pipe is at the same electrical potential as other grounded parts of the system. If the water pipe is interrupted by an insulating fitting, such as a plastic coupling, a bonding jumper must be installed around the fitting. This jumper provides a continuous path for current to flow, even if the water pipe is interrupted. Thirdly, consider the grounding and bonding of electrical equipment. All electrical equipment, such as appliances, motors, and transformers, must be properly grounded and bonded. The equipment grounding conductor provides a path for fault current to flow from the equipment back to the electrical panel. This conductor is typically connected to the metal enclosure of the equipment. In some cases, the equipment may be double insulated, meaning that it does not require a connection to the equipment grounding conductor. Double insulated equipment is designed with 2 layers of insulation to prevent electrical shock. Fourthly, let's talk about ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect small amounts of current leakage and trip the circuit, preventing an electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. They are particularly important in areas where there is a risk of water exposure. GFCIs work by monitoring the current flowing through the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between the two currents, the GFCI will trip the circuit. This indicates that current is leaking to ground, which could be a sign of an electrical fault. Fifthly, let's discuss surge protection devices, or SPDs. SPD are devices that protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line disturbances. SPD work by diverting excess voltage to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the main electrical panel and at individual pieces of equipment. They are an important part of a comprehensive electrical protection system. Sixthly, let's talk about the importance of regular electrical inspections. Regular electrical inspections can help to identify potential problems before they become serious hazards. A qualified electrician can inspect your electrical system to ensure that it is properly grounded and bonded and that all components are in good working order. They can also identify any code violations or safety hazards that need to be addressed. Seventhly, let's delve into the specific requirements for grounding and bonding in agricultural buildings. Agricultural buildings, such as barns and livestock facilities, present unique challenges for electrical safety. The presence of moisture, dust, and corrosive substances can increase the risk of electrical shock and fire. The NEC has specific requirements for grounding and bonding in agricultural buildings to address these challenges. These requirements include the use of corrosion-resistant materials, the installation of equipotential planes, and the use of ground fault protection. Eighthly, consider the grounding and bonding of sensitive electronic equipment. Sensitive electronic equipment, such as computers, servers, and medical equipment, can be particularly susceptible to damage from electrical noise and voltage fluctuations. Proper grounding and bonding are essential to protect this equipment from damage. In addition to the standard grounding and bonding requirements, it may be necessary to install isolated ground receptacles or dedicated grounding systems for sensitive electronic equipment. Ninthly, let's look at the role of the authority having jurisdiction, or OJ. The AHA is the local electrical inspector or other official who is responsible for enforcing the NEC. The AHA has the authority to approve or disapprove electrical installations and to require corrections to any code violations. It is important to work with the AHA to ensure that your electrical system meets all applicable codes and regulations. Tenthly, let's focus on the importance of documentation. Proper documentation of your electrical system is essential for maintenance and troubleshooting. This documentation should include a wiring diagram, a list of all electrical components, and a record of all inspections and repairs. This documentation can be invaluable in the event of an electrical problem. In conclusion, grounding and bonding are complex but essential aspects of electrical safety. Understanding the principles of grounding and bonding and following the requirements of the NEC can help to prevent electrical shock and protect people from harm. Always work with a qualified electrician to ensure that your electrical system is properly grounded and bonded. The proper implementation of grounding and bonding techniques contributes significantly to the overall safety and reliability of electrical systems. Furthermore, it's important to discuss the specifics of ungrounded systems versus grounded systems. Most electrical systems are grounded, meaning that one of the current carrying conductors, typically the neutral, is intentionally connected to earth. This provides a reference point for voltage and helps to limit voltage surges. However, there are some applications where ungrounded systems are used. In an ungrounded system, none of the current carrying conductors are intentionally connected to earth. Ungrounded systems are often used in critical applications where a single ground fault should not cause a disruption of power. For example, hospitals and industrial plants may use ungrounded systems to ensure that critical equipment continues to operate even if a ground fault occurs. However, ungrounded systems are more susceptible to voltage surges and require careful monitoring to detect ground faults. Ground fault detectors are used to monitor the insulation resistance of the system and to provide an alarm if a ground fault occurs. Another important aspect is the concept of impedance grounding. In some systems, a resistor or reactor is intentionally inserted in the grounding path to limit the amount of fault current that can flow. This is known as impedance grounding. Impedance grounding is often used in medium voltage and high voltage systems to reduce the stress on equipment during a ground fault. The resistor or reactor limits the fault current to a level that is below the interrupting rating of the circuit breakers. This can help to prevent damage to equipment and to improve system reliability. The value of the impedance is carefully selected to balance the need to limit fault current with the need to provide adequate ground fault protection. Let's talk about the NEC requirements for specific types of grounding electrodes. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes. Each type of grounding electrode has its own specific installation requirements. Ground rods must be driven into the ground to a depth of at least 8 feet and must be spaced at least 6 feet apart. Ground plates must be buried horizontally in the ground at a depth of at least 30 inches. Metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet and if they are electrically continuous. Concrete encased electrodes, also known as UFA grounds, consist of at least 20 feet of bare copper conductor encased in concrete. The concrete must be in direct contact with the earth. The NEC also specifies requirements for the size of the grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor. It is important to ensure that the grounding electrode conductor is properly sized to safely carry the maximum fault current that could occur in the system. Let's also elaborate on the importance of bonding in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dusts are present. These locations require special precautions to prevent explosions and fires. Bonding is particularly important in hazardous locations to ensure that all metallic parts are at the same electrical potential. This minimizes the risk of sparks, which could ignite the flammable materials. The NEC has specific requirements for bonding in hazardous locations, including the use of special bonding fittings and the installation of equipotential bonding planes. Equipotential bonding planes are used to create a common ground potential throughout the hazardous area. This helps to prevent the buildup of static electricity, which could also cause sparks. Now, let's discuss the specific requirements for grounding and bonding in healthcare facilities. Healthcare facilities, such as hospitals and clinics, require particularly stringent grounding and bonding to protect patients and staff from electrical shock. The NEC has specific requirements for grounding and bonding in healthcare facilities, including the use of isolated power systems and the installation of ground fault monitoring equipment. Isolated power systems are used in critical care areas, such as operating rooms and intensive care units. These systems isolate the electrical power from ground, which helps to prevent electrical shock. Ground fault monitoring equipment is used to continuously monitor the insulation resistance of the electrical system. If a ground fault occurs, the monitoring equipment will provide an alarm, allowing the problem to be corrected before it causes harm. These more technical aspects further emphasize the critical role that grounding and bonding play in ensuring the safe and reliable operation of electrical systems across a broad spectrum of applications. The knowledge is essential for electricians, engineers, and anyone involved in the design, installation, or maintenance of electrical systems.